and have all this very nice interaction. So today I'm going to discuss the current flow in pulsar magnetospheres and essentially think more carefully about the role of twist, which appears to be present in several applications. But I think that there are some interesting results that I would like to share with you. So, right. So a brief outline of my talk. I'm not going to give a very detailed introduction in neutron stars, because I'm sure you are familiar with the basics, obviously, but I'm going to discuss in detail the Goldreich-Julian model, which gives us the basic framework on how we are going to understand the pulsar magnetosphere, and then introduce the ideas of light cylinder and current seeds. And then we will start to see how these basic concepts are changed by introducing twist, and then how we're going to revisit the spin down rate and the torque exerted on neutron stars. Finally, we're going to investigate the location of the inner point of the current seed, still in the axisymmetric mode. And this could give us probably a hint about pulsar moding. So this is basically based on a series of 4 papers, mostly with collaborators from Greece. Dimitris Karagiorgopoulos was a postdoc in our group in Durham, and then we collaborated in Patras. And Dimitris Dotsikas is a PhD student in Patras, and I think that the other collaborators you may have heard of. Now, the basic idea now about the Goldreich-Julian model. So immediately after the discovery of pulsars in 1969, there was a discussion on what is the magnetosphere, what is the magnetospheric structure of the pulsar. So the simplest idea one can have is that the pulsar is, let's say, a magnet that is rotating in vacuum. Obviously, if you think of this concept, then you can have some magnetic and electric field. It's essentially a textbook exercise, not a very easy one, but it's doable. But then, if you start to think more seriously, and you consider that we have the neutron star here, and as it is rotating, we will have, let's say, a magnetic field, but because of rotation, we will have an induced electric field. Now, the force of the electric field on the charged particles on the star will be higher than gravity. So what this means is that we are going to feel the region near the neutron star, near the rotating neutron star, with charges. So essentially, we will have a magnetosphere that is full of charges, and this is actually the other extreme from the vacuum magnetosphere. Now, in this model also, we assume that the neutron star magnetic field is dipole. This is for the sake of simplicity. Of course, we can explore more different and more complicated configurations. Axisymmetric, like having the rotation axis to coincide with the dipole axis. And then another important concept is that the magnetosphere is co-rotating with the star. Now, what this means is that if you think of these field lines that are over here and they are connected to the star on both ends. So here you see the plot up to the equator. This field line will connect from the other side. Both foot points will be anchored on the star. And if we are looking for a stationary solution, then all the points of the magnetosphere of this field line will need to co-rotate. I mean, you can have a solution with some, let's say, sweep back, but they cannot rotate with a different omega here, because then the solution will not be stationary. The field lines now that cross the light cylinder have a very different behavior, because as you can see, because of this co-rotation, the velocity of the field lines will be proportional to the angular velocity of the star and the axial distance from the star. So if you think of the axis, the green line over here, you have this distance. Now, at some point, where actually this axial distance is the speed of light over omega, this velocity v will exceed the speed of light. We call actually this region the light cylinder. Now, this is not problematic because the magnetic field lines are not material lines. So essentially, it doesn't matter. It's like shining a torch, and you see that the beam of the torch, the light of the torch, can move with any velocity if you are far enough. But now, if you think of the particles that are on these field lines, essentially these charged particles that are trapped on these field lines, these are the ones that cannot move faster than the speed of light. So because of this, all the field lines that are crossing the light cylinder, they will have to sweep back. So essentially, a particle on the surface, if you do the mathematics, it's not very complicated, will have a speed that is lower than the speed of light. So there will be a component parallel to the magnetic field line that will be annulling this co-rotation velocity. So this means that the field lines that are crossing the light cylinder will not be allowed also to cross the equator. So this is the equator beyond the light cylinder. So essentially, the dipole that we had initially, and you can think of it that it was something that was where all the field lines were closing, will have two basic regions. One region of closed field lines where both foot points are anchored on the star. And then there will be another region where actually the open field lines extend all the way to infinity. And then at some point, we believe that this assumption, the wind zone, breaks down. There's probably some pressure balance over there, and then the closed field line, these open field lines return back. Now, because the field lines will have this tangential discontinuity over here, there will be a stream of outgoing field lines and a stream of incoming field lines over here. We will have a current sheet on the equator. So the reason for that is that if these field lines were crossing this location here, and they were still co-rotating, they would have to the particles that are trapped on them would have to move faster than the speed of light. So formally, at the equator, we have this current layer. Now, there is a second current sheet shown here in green, which is separating the open field lines and the closed field lines. Now, as we said before, the open field lines are swept back, so they will have a phi component. You can think of it as a component normal to the screen. And then these field lines over here will not have any sweep back. And essentially, there will be a discontinuity between between the B phi component. Because of this discontinuity, there will be another current flowing on this green region, we call it the separatrix, which is essentially poloidal, and because of this discontinuity. So essentially, we have the equatorial current sheet, and then we have also the separatrix current sheet. Now, I apologize for a few slides with some equations, but let's get now to the mathematical formalism, because now we are trying to introduce this equation. So essentially, we can think that this system will go in an equilibrium if, let's say, the electric current density crossed the magnetic field in the comoving frame where the electric field is zero, so that was the magnetic field, is equal to zero. Now, if we think of the lab frame that is not co-rotating, we will have an electric field, an electric charge, and then this entire term is going to be zero. We can calculate the electric field through through Maxwell essential equations, and also connect the electric fields to the magnetic field. Now, going one step further and expressing the system for an axisymmetric configuration, we can write the magnetic field in terms of two scalar functions. Psi is the poloidal flux, and A is essentially something related to the toroidal field, or if you want, is the current that goes through the poloidal current that moves on the field lines. Now, if we do this exercise, we substitute the magnetic field into equations that we had before, and we do some rescaling in the coordinates so that one is the light cylinder. what we get is essentially this equation. So this is the Goldreich-Julian equation that was developed in 1969. And there have been several attempts to solve for this equation and understand the magnetospheric structure. And actually, if you search in the literature, there will be papers from the 70s, the 80s, and the 90s, and all several big names of astronomy at that time were trying to solve this equation with some very nice titles in some of their papers. Now, the problem with this equation is that people in MHD have this type of problems for force-free magnetic fields. But what you see here is that we have this function psi that we are trying to solve for, and this function A, you can think of it as the current that is flowing. Now, what you see is that we have one differential equation, partial differential equation, and we have two unknown functions. So the standard approach that was done for non-relativistic problems is to choose a value for A, plug into this equation, and then solve for psi. Now, this was working for some very special cases, but maybe not so realistic. One was the so-called split monopole, but it was giving some kinds of discontinuities. Now, this problem goes away if we realize that essentially this equation is in principle two eigenvalue equations. So what we want to do is that we want to solve this equation both inside and outside the light cylinder, and then match the solution. So essentially now, instead of having, let's say, one problem of solving the equation for the whole domain, we have two equations that we are trying to solve, one for the interior and the other for the exterior. And then what we want to do is these two solutions to match with each other in a smooth way. So how one can do this numerically in principle is that we can choose a trial function, A of psi, solve on either side of the light cylinder. Then if you see on the light cylinder, this x should be 1, so all this term will disappear, and we have this regularization condition in this spot here. And then solve on either side and try to match the solutions. If the solutions do not match perfectly, so they are not continuous or they have some kinks, then we need to go back to the previous approach, to the previous step, and repeat until this is going to converge. In general, it's not guaranteed that this method will always converge because the equation is nonlinear, but in practice, if it reaches a solution, we know at least that we have found a solution of the problem. Now, another important point is that, as we said before, we need to place somewhere the current sheet, and we do so at the point where the current sheet, where the light cylinder starts. Well, at the same time, in the standard pulsar solution, there is no current in the closed field lines. So if we are to implement this problem here, we are starting with a dipole field which puts no current in the solution, and we repeat this process. And what you actually see through this method is that the system will actually eventually reach the pulsar solution. You see here that it takes some time for these points to be smooth. Essentially, we are solving the equation in this domain and this in that domain, and we are trying to match the solutions. Now, by solving this equation, we also get a value for this quantity that we call A. Essentially, it's the current that flows on these field lines and is required for them to cross the equator smoothly, the light cylinder smoothly. Now, once you do that, you actually find that this A psi takes this function, this form, but then it has to go immediately to 0 at this point, the separatrix over here. And this is where this current sheet we were talking before appears. Now, this current that we had over here is essentially described through this step function. And you can think that the current density there is essentially the derivative of this step function, which is practically a delta function. So essentially, this is telling us that the poloidal current that goes out should return through the separatrix. Now, the big problem is how we are going to deal numerically with this discontinuity, essentially. So obviously, mathematically, you can write an equation with a delta function, but then when we try to put it in a computer, it's not the easiest thing in the world. So in several numerical implementations and in the first solution by Kondopoulos and several others, like the one by Timotin, for instance, what they assumed is that the current sheet, it's not very clearly seen here, returns through the interior of the separatrix. So essentially, they assume that it goes here, and then somewhere inside this region, it returns. And at the same time, instead of having a delta function, it was spread to something like a Gaussian. Now, if we when we tried to take a different approach, we said that, well, this gives us a mathematically acceptable solution. In reality, the current should not come through the exterior because it will have to cross these field lines, whereas in principle it should be parallel to them so that it stays force free. So essentially, we decided to make this expansion at the exterior of the field lines. Now, this had an important consequence, so you have to pay a price for that, because essentially the regularization condition is not perfectly satisfied very close to this region, and you actually see this protrusion. Essentially, if I zoom into this region, that appears. So instead of the last closed field line to follow, let's say, a smooth path, at the same time it's expanding over here. The reason this is happening is because essentially we have spread this layer instead of having it as a narrow region. Now, the second question is whether actually this is understood or seen by some other calculation. So there are in practice three approaches in this, or actually four approaches in these problems. One is the approach of this solution that we have shown before, that one looks for equilibrium solutions of the differential equation. The second one is the MHD approach, where actually we load the magnetosphere with a very small amount of mass, then we introduce some rotation and we try to see how the system is going to evolve. Then there is the approach of force-free electrodynamics, which is introducing some rotation and finding the solution. And over the last few years, we started having results of particle-in-cell simulations. So in all other methods, well, actually in the force-free electrodynamics and the MHD approach, what was happening is that the Y point, so the last closed field line, was exactly at the light cylinder. In principle, in the first problem that we solved, we actually choose where to put it. It was, let's say, a free parameter. Now, when they started solving this with particle-in-cell simulations, where actually the resistivity of the other problems of the other approaches was significant, they found actually the following, that the magnetosphere is not closing at the light cylinder. So here in their units, in a paper by Hu and Beloborodov, is 6. It's not closing at 6, but it closes at around 5.2. So it's about 87% of the light cylinder. The second thing they observed, these green lines are the poloidal magnetic field lines, is that they are much denser over here, just before the last closed field lines, and much broader there. So essentially, the last few closed field lines will have a very strong BZ magnetic field compared to the magnetic field, to the BZ magnetic field that you have over here. The reason this is happening is because at the orange field lines, we have a B phi component that disappears. So because the system wants to be in some pressure equilibrium, it's trying to compensate by having a stronger poloidal field just at the interior. But still the question, why the particle-in-cell simulations find this the last field line not too close at the light cylinder, but at 0.87 of the light cylinder, is still open. In principle, using this method, one can essentially move the inner edge of the current seat wherever you want. You can put it closer to the star. It's just a function, a matter of choice. So what we did is that we did a calculation where actually we started moving the inner edge of the current seat closer to the star instead of having it in the light cylinder. And actually what we noticed is that, first of all, when we try to move it very close to the light cylinder, that the BZ component of the field was rising. So in principle, this means that the BZ field, if we put it exactly at the light cylinder, will become singular. Whereas if we move it deeper in, if we move the deeper in, it will become weaker. Now, this is perfectly consistent with this particle in cell simulation, though our method is less computationally intensive. And then at the same time, what we did is that we tried to estimate if there is an energy minimum in this region. So actually what we found is that if we estimate the amount of energy that exists in the magnetosphere, and in principle, because all the magnetosphere extends to infinity, so we evaluated the energy from the star up to two light cylinder radii, we found that there appears to be an energy minimum around at 90.92 of the light cylinder. Now, what is interesting here is that, okay, we didn't get exactly the number that they had in this simulation, but clearly, as we move the y point closer in, essentially we get less energy in the magnetosphere, and this would be energetically favorable. What will be now, though, the price that we will have to pay for that is essentially that we will have a current sheet that is inside the light cylinder, which is mathematically acceptable and physically acceptable, but not required. So the current beyond the light cylinder is essential. This one is not essential. So this may be prone to instabilities, and we will discuss these implications a little bit later. So comparing the two solutions, essentially this is the solution with the light cylinder, the y point at the light cylinder, and this is further in. Actually, visually, they seem to be very similar, but actually here we have many more field lines to be open compared to the other case. Now, I'm moving to some other part that is relevant, because we haven't dealt yet with this region here where we have the closed field lines. So several models, and essentially magnetar models, usually assume that the magnetosphere is twisted. Now, you can twist the magnetosphere if you want to, of course, and if it's a if the system is non-rotating, you can twist it globally. However, if the system is rotating, if you try to twist the magnetosphere in the open field lines, this twist essentially will go away in the form of some kind of electromagnetic wave. Whereas now, if we twist this region here of the closed field lines, right, that we have in this region here, because both foot points are anchored on the star, you can think that there is a symmetric picture just underneath. Essentially, this twist will stay here. Now, but by twisting this region, we find actually that there are two important consequences. And just to be sure that we are not being fooled by choosing a very particular case, we chose different profiles, essentially linear and nonlinear ones, with a function of the twist being A times psi minus psi naught. Psi naught is the flux at the last closed field lines raised to a power. So this has been linear, n has been 1.2, and n has been 2. So actually, by introducing twist, we notice that two things are happening. first of all, more field lines open, so the system tends to have a larger magnetic flux crossing the light cylinder. And then at the same time, the solution was enforced to move, the closed field lines were forced to move closer in. So actually now, instead of having the choice of putting the Y point at the light cylinder, we cannot find physically acceptable solutions by having the Y point at the light cylinder. The solutions actually required that the Y point was further in. And the more amount of twist we were introducing over here, we had a higher number, a smaller region. Then when we tried with higher end, let's say 1.5, 4, and this should have been 5 actually over here. I should have put the other figure. You see actually by increasing the twist, the system the closed field lines become more concentrated. And then by increasing also the nonlinearity of the distribution of twist, we reach a point where actually this twist, the system almost reduces to a split monopole. Now, what is interesting here is that we get a split monopole by only introducing a twist in this smaller region. But we introduce a lot of twists. So essentially, what happens here is that we shear the field lines by about pi/2 in a small region. And then these field lines cannot cross any longer the light cylinder. So what this means essentially is that even some changes happen near the surface of the star, this can affect the global structure of the magnetosphere. So essentially, these local phenomena that we see sometimes in these magnetic field simulations of magnetars, they are not shadowed by the large-scale dipole magnetic field, but essentially they affect it if we introduce rotation. If we didn't have rotation here, then we would have had something that was an arcade, a highly twisted arcade, but the rest of the field would be quite similar to a dipole. Now, I'm going to explain why we are forced to have the field, the Y point moved in. So essentially, since we are the location of the Y point is essentially where we put the inner edge of the current seat, and this is something that we can explain we can choose actually through our equations. We can ask the code to essentially say that the current sheet will start from here, and in this region here, so from r less than 1 and deeper in, we will have a magnetic field that is vertical to the equator, as is the case for the rest of the system. Now, what you see here is that by introducing some twists, so this is for C equal to 1 and N equals 2. Essentially, what happens here is that the system is trying to maintain some equilibrium, and it starts producing field lines in this region here that would look like that they are completely disconnected from the star. So essentially, while this is a mathematically and numerically acceptable solution, it's not physical because it has all this region here that are field lines that are not connected to the star and they are rotating. So maybe you can have this region, let's say, as a plasmoid for a short time, but then if you want the system to relax to some equilibrium, you can have twisted things that are not connected to the star. Now, if we try to calculate the implications of these quantities, we actually see by introducing a twist of up to 1.5 radians for the various models that the magnetic flux function of the last closed field line increases drastically. So it can even increase by a factor of 5 for the nonlinear models. And then this will lead to an increase on the spin down power by a factor of 25. So this is by introducing a twist of pi/2. At the same time, the polar cap size will expand because essentially the last open field line is moved further in. So since the last open field line is moved further in, there will be a much larger part of the star having open field lines. In the extreme case of the split monopole, of course, the entire hemisphere will be the polar cap. Now, these values here are based on the assumption, because this was the simulation, that the approach in the simulation that we took, that the light cylinder is 10 times the radius of the star. In reality, especially in magnetars, the light cylinder is probably 1,000 times the radius of the star. But still, the argument will hold, though, for much smaller polar caps. So, in terms of pulsar activity, in the untwisted magnetospheres, I think that an important point to keep is that we have this energy minimum with a current sheet within the light cylinder, and then another state where there is no current sheet inside the light cylinder, but it's not a minimum. Now, the energy minimum state that has this current sheet is prone to resistive instabilities, because this current sheet is there, but it may tear. Whereas the current sheet at the exterior, even if it tears because of some instability, it will have to form again, because you can't have in a steady state solution field lines that are actually crossing vertically the equator. Now, so if we try to see now the implications by getting the comparison of these two states, switching from one state to the other will expect to change by about 20% P dot, by practically having more field lines closed. And we seem to have two states that are kind of well defined. So it's not that we have a complete freedom of putting the current sheet wherever we want. Now, in the twisted magnetosphere, we have a free parameter that we put in the game. And then increasing the twist, we have more efficient spin down. Now, if you increase it as much as you want, we can get spin down rates of higher than factor of 10, but maybe this will be in transient states. And the other thing that is important is that it's sufficient to have only finite twist for the entire system to reach to the split monopole. This is pi/2, which is also consistent with some of the calculations that were done a few years ago, I think by Tanner and Daniele, probably, that you were finding this limiting case. So this limit holds also in the relativistic system. Now I'm going to my final part of my talk. And the question now that I'm going to discuss briefly is, okay, we have all these magnetospheric currents. How do they close? Obviously, if you have a circuit, you need somehow to close the circuit, and they should close somewhere through the crust. Now, the second bit that we have the currents in the in the closed field lines. These are actually currents that are produced from the interior to the exterior. So I'm not going to discuss this, but I'm going to discuss the first family of currents on the open field lines. Now, these are important because these currents are responsible for the spin down of the star. So essentially, we need to see where exactly on the star we exert the torque that spins it down. All right, so you have something that's 1.5 polar solar masses, and you spin it down and you put some torque somewhere. Where do we put this torque? Right. Now, the problem set up for this, for the usual case, is if you want to solve for a circuit, it's again like undergraduate physics, is that you put the voltage, you generate an electric field, you know the resistivity and the resistors and everything, and you get the current. Now, what we have here is the opposite problem. We know the current of the magnetosphere for the system to maintain its force-free equilibrium, and then we want to see how it's going to flow through the star. Now, this is a little bit not so counterintuitive to what we have been doing. So essentially, we have the current going out, coming back in, and then somewhere here, if we zoom in this region, it should close and exert some torque. Now, the question is, does it close going all the way to the core? Does it close on the surface? And what does it really happen? Now, the way to solve this problem gets us back to some basic circuit theory. So essentially, we can think of the magnetosphere being this big resistor that is responsible for all these currents go to infinity. And then we are going to think of the crust as these two smaller resistors that are on the surface of the star. Obviously, it will be a continuum, and we will show how this is going to be solved, but I'm using this for illustration purposes. Now, if the R capital, R without index is much higher than R1 and R2, then essentially the total current will be mostly sensitive to the value of this R and less sensitive to this value R1 and R2. But I1 and I2 will depend on R1 and R2. And we know actually from whatever you call it, I1 times R1 is I2 times R2 because the difference of the voltage here and there must be the same. However, another way to approach this problem is to say, okay, I1 and I2 has to be equal to the total current, and then the power that is released through these two resistors, the ohmic power, will be I1 square R1 plus IT minus I1 square. And if we want to minimize it, what we actually get is essentially this relation. So actually the current will follow the path through the resistors that minimizes the ohmic power consumed. Now, if we try to do this on the star, what we're going to say is that we have this current flow. The current flows through the crust. We know the resistivity of the crust. We do some minimization principle, like applying this, let's say, Fermat principle that we had before. And eventually we get an equation for the curl of the current over the conductivity to be zero. Writing down now this equation, we get this expression that can be easily solved numerically, provided that we know the distribution of the current on the surface of the star. But we know the distribution of the current on the surface of the star because it has to be force-free. Once we go, though, inside the neutron star, the current is no longer force-free because it has to spin down the star. So then, by solving this equation for I, we can get the distribution of the current inside the star. So actually what happens here is that the current goes out through this region all the way to infinity. And as we said before, since most of the current will return through this narrow region and the separatrix, it will come in through this point, and then the solution of this equation will determine how deep it will penetrate. So here I'm plotting the torque, and whereas most of it is blue because it's essentially spinning down the star, there are some regions over here where actually it's trying to spin up this part of the crust. Now the net effect is spinning down, and of course it is consistent with the spin down power that we get. What is interesting though is that if we start putting some relatively long periods like we do here, let's say 5 seconds, that the depth where actually the current penetrates, you see that all this from 1 to 0.9 is the thickness of the crust, is very small. It's something in the order of 50 meters to 100 meters. So in practice, all this torque needs to be exerted in a very small region, in a very small depth. Now, we need to comment on the fact that we made the assumption that the ohmic power here is much less than the ohmic power, than the spin down power. And we have done this calculation. And indeed, the ohmic power that is consumed here is much smaller, is about 10 orders of magnitude at least in this region. Yet there we expect to get some ohmic power on this rim of the polar cap over here because we have a very high current density. Now, if we are to push this idea to an extreme, though, is okay, let's go to the most strongly magnetized neutron star that we know of, assume that it is a dipole and so on, and then try to see what's the structure of the current. Now, what you actually see here is that it only goes down by about 100 meters. And you can see here that the part that is down there, if you compare it, because essentially the crust of a neutron star, you can think of it, it's at least the outer part as a Coulomb lattice, it will have some maximum stress that it can tolerate. So actually this region here, the last 20 meters probably, they will be prone to crust breaking because it will compare the stresses that appear here to the critical values. You see actually that for this entire region down to this point, probably the last 30 to 30 meters, are not well coupled. So essentially, this means that for strongly magnetized neutron stars, maybe at several cases we have these bits that are completely decoupled, and we get most of the spin down torque in this region here, which is actually smaller than the entire available torque that we could have had. Now, I'll move to my conclusions. I've discussed more or less problems about the currents of the pulsar magnetosphere. So we started with the standard magnetosphere in the axisymmetric case. What we are actually saying here is that this force-free model can be even actually an overestimate if the current closes closer to the star, which is something that could be based on energetic arguments. And then the last open field line may oscillate quasi-periodically between the light cylinder and the minimum energy position. So if this current sheet appears and disappears, and this is a question that we need to address it through a time-dependent simulation, we can have more indications on that. Now, introducing twist in a magnetosphere, and if we do this for the relativistic case, leads to a smaller region of closed field lines. So essentially, these field lines shrink, the closed ones. It's not that it is inflated. Intuitively, one could think that these field lines, this closed region, because you put twist, you think that you put energy, are going to be inflated. But essentially, it has the opposite effect. Since you put more current, they become more tight. Now, the spin down is more efficient, and we can have finite twist to completely open the magnetosphere. And then, thinking of the magnetospheric currents, they must flow somewhere in the crust. And we have proposed a Fermat-type argument to see how deep they penetrate. While most of the results are reasonable, but still it's a good argument a good question to answer. If we think of magnetars that have long periods and high magnetic fields, they will have very shallow currents. So actually, we will need to put this enormous torque near the surface. And now, since the surface could fail at some point, we can have this noisy and erratic behavior. So I'd like to stop here, and I'll be happy to take questions.
Thank you for the talk. Questions?
Yes. Thank you very much. Very interesting indeed. I have a question on your last part. So when you model this,
Yes.
because you, apart from the magnetospheric component of the currents, you have currents in the crust. So
Right.
you have currents that might come from the core. I mean, there are a lot of other components.
Right.
Now, how are they negligible compared to this?
Right. So that's yes.
Could you summarize the question? So
Yes. So the question is that if except for the currents from the magnetosphere, we will also have internal currents. So how are they going to interfere with this process? Okay. Now these currents, in the standard approach, they will close inside the star. So while since they are going to close inside the star, they cannot exert any torque on the star or any net torque on the star. So they can't spin up or spin down the entire star. Yes.
Related to this.
Yes.
So it's true that, let's say, we could render a condition in order for this to happen.
Yes.
But physically, in principle, apart from the fact that nobody is able to actually simulate this, but in principle, they can interact with this force.
Right. Okay. So yes, in principle, and so if I think this would be like probably one of the next steps is to connect so if you allow the internal currents to go out and then come in, then they can also bring their own torque. I don't know if anyone has tried this. I think that Clara only recently did this in that paper, the internal field going to the external.
So do you think more or less would that be negligible in terms of the actual torque in this picture? It might be that even considering this, it's negligible.
I think that yes, I think that the net effect will be zero. Locally, we will have strong stresses, but the sum of these stresses will be added to zero. Probably one can prove that through taking like we did here, the divergence of the J cross B term, but we haven't done that. Yes.
Thank you for the nice talk. Yeah, about the current sheets being inside the cross-free lines.
Yeah.
Firstly, you used to find that outside the light cylinder, there are places where the electric field overcomes the magnetic field, right? Do you observe also this inside the light cylinder?
When we close this region here, no, still the electric field is smaller than the magnetic field, because inside the light cylinder, even with the current, the electric field will be V cross B. So since the velocity here will be lower than the speed of light, the electric field element will be lower than B in this region. So essentially, even in this current, it will have a different behavior.
I have several questions, but I will make one and be the rest of it. In the position of the white point, that whatever it is that we can focus on, how much it is inside. Do you have any feeling of how much the fact that the boundary condition of these simulations at the end are 2 or 3 times the less similar? They're very close to the end.
Yeah, we typically did 6 times the light cylinder.
So,
yes.
Do you have any idea of how much it affects if you put it at 2 or 6? You get the same results?
The results are very similar in either case. So especially when we have the highly twisted ones, because it essentially the condition that we put at the boundary of the box is that of a split monopole, which is based on Goldreich and Julian arguments, but it's a boundary condition. It doesn't change it very drastically. So at some point, out of curiosity, we experimented with something that looks more like a dipole at infinity, and there was a difference by a factor of 10%. Which is not too much, but it shows something. The dipole is unphysical, of course, because it will have problems on the equator, but we put it on the upper boundary. Yeah.
More questions? No, if there's anyone in the Zoom, you can shout if you want to ask something. Okay, if not, let's thank this speaker again. We can go for pizza.
Next option.